Hello, my name is Prithvi and I'm a part of GT Solar Racing.
I'm Mario, I'm also a part of Solar.
I'm Brendan, I'm part of High Tech Racing.
I'm Mikhail, I'm also part of High Tech Racing.
We are Team SCC for Capstone this year. This is our project. It is a motor controller for solar cars.
Georgia Tech Solar Racing is one of many student teams around the globe designing, building, and racing solar electric vehicles from the ground up. Every year, these teams attend the Formula Sun Grand Prix, currently being hosted in Bowling Green, Kentucky, where they take part in a closed-circuit race, and the team with the most laps in 24 hours wins. Every other year, the American Solar Challenge takes place, and students have the chance to expose their cars to the ultimate test, driving on open roads for over 1,000 miles. This year, this event started in Nashville, Tennessee, and went all the way to Casper, Wyoming. Because of the emphasis on distance traveled and restrictions thanks to the limited solar array power, efficiency is top priority in the design of these electrical systems, and it can be extremely expensive to obtain good products to build a competitive solar car.
One of the most important components of a solar car's electrical system is the motor controller, and if you're trying to get the most efficient ones out there, you're going to have to pay over $5,000 in something like this, the Wave Sculpture 22. This specific motor controller comes all the way from Australia, and that's a huge setback if you're trying to interface with the vendor and trying to solve problems for your solar car team, for example. So for new teams that are trying to get something good to complete their system and make an efficient car, this is pretty restrictive, both in terms of support and especially price. So our team identified this as a major setback for new teams that are trying to join the competition, and we decided to make our own motor controller, the high efficiency inverter, which is an open source version of this guy, but 15 years in the future. So this here on my left hand is able to do up to 99.7% efficiency at nominal, output a peak power of 8 kilowatts and a nominal of 3 kilowatt, which is perfectly compatible with everything that this does, but over 10 times cheaper. Our project has three main components: the logic stage, the firmware, and the power stage.
So this is our logic stage. You can see that it has a lot of components, but the main purposes of this are to house the microcontroller, which is the brains of all these operations. It's an STM chip, and the main functionality is to both take in inputs from the other board, the power stage, including current and voltage sensing, and output PWM signals, which is essentially the control signals that are going to the main power stage of the inverter. This also has a bunch of other features that are useful, such as interfacing with the motor itself to know which direction the motor is facing, and also being able to communicate via CAN using different sorts of communication protocols over the rest of the vehicle's bus.
We flash our STM32 with custom developed firmware that we developed completely in-house without the use of existing libraries. It implements field-oriented control, which is a broad technique for controlling synchronous motors, such as the one found in the solar car. With our firmware, we can precisely, rapidly, and efficiently control the motor's power output while simultaneously gathering high-resolution data from the onboard sensors. Our firmware also implements advanced switching techniques, such as zero-sequence modulation, which effectively reduces switching losses in the inverter by 33% as compared to naive space vector PWM. Zero-sequence modulation has the overall impact of reducing the inverter's heat output by 25% without any loss of performance.
The power stage contains 3 half bridges with gallium nitride FETs, as well as the associated voltage and current sensing, and the bulk capacitance and gate drive. Compared to the Wave Sculptor that we are building against, new technologies have come out, like gallium nitride, which is a high electron mobility semiconductor material that allows this to be extremely small while still outputting the same power as the Wave Sculptor.
Considering that our solution costs $500 versus the $5,000 for the Wave Sculpture, we have achieved our main goal, to make an accessible motor controller for solar car teams without sacrificing performance. Now, we will be sharing this initial version with other interested students so that we can continue improving it.